In this video, we'll be learning how to differentiate functions that have more than two or more terms, or some functions where you have complicated, or rather, uh, functions that have uh, like square roots and non-integer powers. So let's look at the first example here. First, we have x minus 2 on top of the fraction and x squared in the denominator. We have to find the gradient of this curve at point 2 comma 0. Now, the 0 is irrelevant to us because we could have substituted 2 into that equation and we would have known that the numerator at point x equals to 2 is 0. So, what do we do to find the gradient? This is where you have actually you can rewrite that expression, simplify it, and you can distribute the denominator of the fraction for each term, for each of the terms separated by the minus sign there. You get 1 over x for the first one, and you can rewrite it as x to the power minus 1. So, and the next term would be 2 times x to the power minus 2. Just simplified first. Now here's where we got more than one term. What do? We simply use the power rule like we did before, and because the question doesn't say from first principles or anything like that, we can just go straight to the power rule and apply that here. So we write dy by dx equals to minus x to the power of minus 2 for the first term, and we continue with the power rule. We pretend that this is just a separate, we just applying power rule separately to each of these terms. So applying power rule here means that minus 2 times minus 2 will be a plus 4, and x will have a new power of minus 3 there. Alright, so now we've got this derivative function. We can simply evaluate it at point 2. That means that sometimes I write dy by dx, and this vertical line with x equals to 2 means that I'm evaluating that expression with substitution of x being minus 2. So we are to evaluate this expression with x being 2. So we're substituting a 2 everywhere we see an x, and we evaluating this expression, which is going to be a quarter, simply a quarter. Right, so in this next example, once again, we actually have a plus c at the end. I'll put that there on purpose. We're going to find the derivative here. So notice what happens here. The dy by dx is going to be 2x for the first term. The next term will have 6 and no x's whatsoever, because when you subtract x power of 1 minus 1, the new power is 0, isn't it? So x to the power 0 is not necessary to be written, because x to the power 0 will be a 1. And what happens to this c here? This constant c has, you could think of it as already has x power 0. There's no x's there. When there is no x there, what you're going to do is bring this power down, and you're going to have a c multiplied by a 0. And if you did think of it as x to the power 0, doesn't matter what this x is, because you're multiplying a constant by a 0, it will simply disappear. You don't need to write anything. Just like we didn't write this x, its derivative is just minus 6. Why don't we think of it and write it? Because you know from your gradient, alright, when you were in year 10 and you were told that y is minus 6x, tell me the gradient, your teacher was just expecting you to give them minus 6. You weren't expected to write minus 6x, were you? You knew this in year 9, 10, 11. You knew how to write the gradient. In chapter 5 and 6, we did deal with gradient of straight lines, and you already knew how to write it. So why would you want to write x to the power 0 here? Is unnecessary. So don't do that. And So let me wipe off my writing here and show you what the answer neatly looks like. So the answer here is the that's a -6 there, and this constant will disappear. So every time you differentiate a constant that doesn't have x in it, don't forget that you're differentiating with respect to x. Okay, the variable that you asked to differentiate with respect to is x. You might have a function in terms of t. You'll see other functions in mechanics and motions of velocity and acceleration are defined in terms of t. So if you had a t, then you would differentiate with respect to t. But let's leave that discussion for another time. We were talking about constants here, so the constants disappear. So the final answer in this question, this is the same example. Now I'll put a -4 rather than c there. All right. So if you have this differentiation to do, the first term will give us 2x, the next term is -6, and that's it. You don't need to write anything else. That's it. All right. So let's look at this next example. We've been told the formula for y is x cubed plus x squared, and we are to find the gradient of the curve at x equals to 2. Therefore, you simply apply the power rule one term at a time. You get 3x to the power of 2 plus 2x. And that's the derivative function here. Now we are going to evaluate the derivative function at x being 2. So we substitute 2 wherever we see an x, and we find the answer is 16. That is the gradient at that point. For this example, we have fractional powers, and we are to differentiate it at point x being 1. Notice it's almost in we are not concerned with the y value. We could have found that by substituting 1 into this expression anyway, so we don't need the y value. All we have to do is find dy by dx first. So we're going to say, what's half times a third? Half times a third is 1/6, and the new power of x should be minus half, because we're subtracting 1 from there. And the new coefficient here is 2 times 4, which is 8, and the x will have power of 1, which will leave it like so. Now I can draw a vertical line here and say, let's evaluate this expression at x equals to 1. So I will have 1/6, and 1 to any power is still 1, and just going to put the power there, 1, and 8 times 1 there. So we will have 1/6 plus 8, which is 8 and 6. Alright, notice they're not multiplying. This is a mixed number, like 49 over 6. Alright, so let's look at the next example. So this final example involves a square root in the denominator, and what we do is, first, before we go into finding the derivative, we write this with power of x. We want to write explicitly what's the power of x. A quarter remains where it is. X is in a denominator, therefore it has a power of a negative a half. Now we are finding the derivative function here. So dy by dx is going to be a negative half times a quarter, which is minus an eighth, x to the power of minus 3 over 2. I'm just going to write minus half minus 1 here, so you know what happened, and then right after that is minus 3 over 2. You can put it in the calculator, work it out. That's the answer there. You can tidy things up and rewrite it like x in the denominator with the power of 3 over 2. That was because that was a negative power here, it was in the denominator. Okay, so even further simplification is possible. You can write it as the square root of x raised to the power of 3, if you wish.